Life. Its origin on Earth is the lifelong unknown scientists have long sought answers for, and space is full of questions waiting to be answered. But what if there's already a group of molecules that could hold those answers, not just for Earth, but the entire universe? Welcome everyone, where today we'll be exploring tholins and why they could help understand the origins of life. I'm Arianna Matson, a student at the University of Florida, and today I'm joined by Jennifer Holt, an amazing science teacher at the State College of Florida Collegiate School, who was awarded the 16th Congressional District Teacher Award in 2020 and has graced her presence with us today. Ms. Holt, thank you so much for joining us.
Thank you for having me.
Of course. Can you first explain to us what tholins are?
So tholins are this kind of tarry substance. They tend to be reddish in color, and they are kind of the building blocks to make more complex molecules that will turn into organic molecules, things for life. So they're like the precursors for the building blocks of life. So tholins are kind of neat because we are looking at things like, for instance, all of our building blocks for life, schnapps, right? So you've got carbon and hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So all of these things we know we need for living beings, right? To create things that are alive, plants, animals, bacteria, anything. But you can't just put them together and make them alive. Most of those compounds want to make what are called inorganic compounds, things that are not alive. And so to put them into more complex structures where we can start to build amino acids and proteins and DNA, which are required for living things, we have to give them a little kick in the behind, right? They need more energy to start building things that are a little bit more complex. And so that's where radiation from things like the sun come in. And so if you have these very simple compounds that are put together inorganically, so things like methane and ethane and nitrogen gases and things like that, we can start to take the energy from the sun, UV radiation, and we can have those be those energized, and they start to build what are called tholins. So tholins are different depending on what kind of gases you have, the abundance of those gases, and the amount of radiation that you're receiving. So tholins is kind of like, let's say, a salad or a pizza, right?
Yeah.
So you've got tons of different kinds of pizza. You have supreme pizza, you have pepperoni pizza, you have veggie pizza, right? But all of the components are different depending on what kind of pizza you're going to make, right?
Mm-hmm.
And so tholins are kind of the same way. Tholins is like this catch-all phrase to describe these different kinds of compounds that are that interact with UV radiation and make a more complex soup, if you will. So when you're talking about tholins, you can have tholins that are tholins that you find on Pluto or tholins that you find on Titan, right? So they specifically will name them like Titan tholins or Pluto tholins or Europa tholins, right? And so all of those different groups the tholins are slightly different in their composition, depending on what was there when those particular molecules interacted with the UV radiation to make more complex things.
That is quite interesting. Yeah, that tholins are so unique depending on where they're made. Does that also mean that they're unique just in the lab as well when people are trying to replicate them?
They are, because and we usually just call them lab created tholins, but depending on what gases you're putting in to begin with, you're going to get different compounds that come out of that. But all of those compounds are going to be basically different alcohols, if you think about it that way. So different kind of alcohol compounds that are then being used to be able to create things like amino acids, and then going down the chain, right? Eventually to RNA and DNA, which we need to make living things.
That is so fascinating. Okay. Well, you did mention that tholins tend to be reddish in color, and there have been a lot of planets and moons observed by telescopes or by probes that tend to have reddish streaks on them, or how Jupiter has the little spot that makes a storm that's red. Are there potentially tholins on those planets and moons that people have observed or hypothesized that you could maybe dive into?
Sure. Yeah. So we have a lot of places in the universe that we first thought were iron oxide when we looked at it, because we have been studying Mars, right? A lot. And so I remember when I was younger, Mars, we were just starting to explore it and sending probes and things like that. And so we were very excited because we were excited about the presence of water and all that. And then we figured out that it's iron oxide on the surface, right? So then when we looked at anything red in the future, we're like, oh, it must be iron oxide, right? Yeah, it must be. And then we started looking at this idea of tholins and started to realize, well, maybe this is another possibility, but it wasn't really talked about a whole lot at that time. It's really come into its own now. They actually started doing experiments with it in the 50s. And the first energy source that they put into it in the lab was plasma. So lightning, because they thought, with Earth and all its storms and things, that lightning may have been the strike that started life. And then Carl Sagan in the 70s decided, well, what if we don't use plasma? What if we used just straight UV radiation instead? And it produced the same kind of things. So, but all of that was really new at that point in time. So it wasn't really talked about a whole lot. And in the sense of, oh, this red stuff on other places could be tholins. We just didn't put that together at that time. And now it's being put together much more, especially since we've now confirmed tholins on some bodies as well, which is very cool. So we're looking to confirm on other places. So one of the places is Europa that we were looking at and trying to say, well, maybe this is tholins. We're kind of thinking now, maybe it is kind of a second level of tholins. So Europa is kind of unique in the fact that it's this icy little moon, right? You always want to call it a planet because it's got so much in common with planets, and it's just fascinating. So excuse me if I call it a planet. It's this little moon of Jupiter, right? That is so close to Jupiter that it has this tidal bulging going on. So it's basically expanding and contracting always. So it's got this heat that's being built up inside of it. And we do know that it has a saltwater ocean underneath. And so all these, but the surface is very icy, it's frozen. Mm-hmm. And it has a little bit of a oxygen atmosphere, but it's very tenuous. It doesn't stay there very much or very long. And so we think it's actually coming from water vapor that is being kind of let out of these cracks. So we've got all of these stripes and everything, like these striped cracks that are actually very weird and geometrical, right?
Yeah.
And so you can kind of see that it kind of expands out and there's these lines that it kind of builds on itself. So it's almost like that tectonic plate movement where things is coming up from the inside, but in this case, it would be water, right? Water vapor from the warm, salty ocean coming up. And along those lines, you've got this reddish substance, which at first we theorized as tholins. And we said tholins are very, very different no matter where you go.
Yeah.
Most of the time when you encounter tholins, you're looking at methane or ammonia, things like that, nitrogen, hydrogen, and carbon-based things. Now what they're starting to figure out on Europa specifically is that they think there's a lot of salts and sulfur in those lines too. So it may be that the stuff that's coming up is being hit by the radiation from Jupiter since it's so close. Mm-hmm. And it's actually making a different kind of tholin based with the sulfur as well, which is kind of interesting.
Interesting. So it's just like the next step in the recipe for organic compounds is just
it's like
coming up from the water and then and also radiation.
Yeah.
Okay, got you.
Yeah. So that's one that we need to look more at. And we actually have a mission that is going that way. So the Europa Clipper, if you're familiar with that, they just recently launched it in 2024, and it's going to be arriving about 2030, the year 2030. And so they're actually going to be looking at all of that compositions. So I think they had 3 things they were looking for. So in those habitable conditions, they're trying to look at the ice shell, the actual composition of it. Because of those red streaks, they're trying to figure out exactly what it is. They're thinking from first glance it may be sulfur and salt driven, but they're not sure. So they're looking at that. They're also going to look at how deep the ice shell is, what that cap is on there, looking at the composition of the ocean, and then looking at the overall composition of the planet to confirm that what they think is already there, like the core and all of that, and then the geology as well.
All right. Well, perfect. So we've got a Jupiter moon that definitely probably has Tholins on it. There's also the Titan moon that circles Saturn, and that one is actually very well known. They had a couple missions in the early 80s called Voyager 1 and 2, and they were able to find traces of certain compounds that would need to be made with Tholins, like ethane and propane. But they were only sure that it was in the lower atmosphere until the Cassini spacecraft was sent in about 2004. And it was able to discover that there were contents of nitrogen, methane, and benzene as well in their higher atmosphere, over 1,000 kilometers from the surface. Is there anything from discovering that would make scientists pretty sure that there's tholins and that there's something else going on in that atmosphere to make that happen?
Yeah, they've actually confirmed that there is a Tholin haze on Titan. So that's that. When you look at Titan, it's very hard to see what's at the surface because the atmosphere is so incredibly thick, and you can see it in that haze. It's a reddish haze. So oftentimes we think about tholins, on the surface of something, but it can very well be in atmospheres as well, right? We find it in ices, we find it on surface of things, and we find it in atmospheres. And so we've actually been able to confirm that, yes, there are tholins in the atmosphere of Titan, right? In this haze that's surrounding the little moon there. They're also fairly certain that there are tholins on the surface of Titan as well. And so one of the missions that they're sending looks to confirm those things as well, right? To confirm that there are tholins on the surface and perhaps even in the lakes of methane there as well. So having these building blocks for life there. There may also be life there already, just in a very different form than we are used to as well.
Right, because you just said there's methane lakes on the surface, correct?
Yes, there are. So the rivers and lakes, it actually has a methane cycle instead of like our water cycle, right? So we have the evaporation, precipitation, all of that. They have a cycle too, but instead of the water cycle, theirs is the methane cycle. And the gravitational force on Titan is much, much less than on Earth. So when that methane cycle happens, it falls very, very slowly, right? And so you have it almost be like rain in slow motion here. And the drops are really, really large because you don't have all of that pulling and making them smaller, which is kind of cool.
So we now know that there's a few moons in our solar system that very likely have tholins. Is there any other general place that we've kind of theorized or found them to be on? Like maybe a planet or something like that?
Yeah, we have so New Horizons, when it went by and did a flyby of Pluto and Charon, and then on to Arcturus, and now it's on into our outer Kuiper belt. When we flew by there, we were able to see those same tholins on the surface of Pluto and also on the surface of Charon, which is the moon of Pluto. You could almost call them a binary planet because Charon is about half the size of Pluto. And so it pulls on it a bunch instead of one just going around the other. They kind of pull on each other and they do this nice little dance, right? So we were able to look at both of those as we flew by. And Charon, which is the moon, has this nice little red cap up by the ice cap. And then Pluto also has it on its ice caps as well as dispersed through the planet. And so we are fairly certain that these are tholins too. We have now figured out that we tend to find them in a lot of ices. So nitrogen ices, carbon dioxide ices, methane ices, which Pluto does have methane ices and nitrogen ices. So the nitrogen ices are kind of unique on Pluto. they actually start as atmosphere when it's closer to the sun. And so you've got this kind of tenuous nitrogen atmosphere. And when it gets further away from the sun, it gets so cold that that nitrogen actually collapses onto the surface of the planet. And so when it's in ice form like that, it can pick up that radiation and start to hold on to those tholins there. You can see them in the methane ices and on the other places on the planet too, which is kind of cool. So we've got them there. We found them on comets in our solar system, evidence of comets having tholins on them. So a lot of these, and it would make sense, right, with comets because they are icy balls, right?
Yeah, just
That
going
are
around.
flying toward the sun. So you've got all of these ices and it's heading right toward the sun. So you've got all kinds of radiation necessary to produce these tholins, right? So they're this tholin rich atmosphere. And it's very nice because as you go through and it loses all of that, right, into space, now it's there ready to hit and bombard other bodies as well.
So like comets are like just easily transportable cooking
Yeah.
ovens or like the easy
Yeah.
bake ovens of Tholins.
It
Yeah, gotcha.
is,
Okay.
right? So you've got these just kind of going around the sun and doing their thing, and then they're leaving all their stuff behind as they say bye, right?
Right.
Or as they're coming toward it.
Mhm.
So it's kind of leaving all of this here too. And all of those things are going to run into other planets, other moons. So comets may be very well our distributing factor for a lot of those tholins too, which is kind of an interesting thing to think about.
Definitely. Well, we've talked a lot about how Tholins tend to be in ice. I mean, they're of course also in the atmosphere and on surfaces. Well, we have a bit amount of ice here on our own planet on Earth. Is there a reason why Tholins aren't here right now?
You think they probably were at one point. But one of the things about tholins is that tholins, to get to their next building block and step, right, they have to have oxygen present.
Mm.
And so once oxygen is present, those compounds can start to reform and make even more complex compounds, right? And do the thing that we want them to do, which is create life. So here on Earth, that has already happened, right? We've cooled as a planet. We have now a wonderful atmosphere that's oxygen rich, and we have something called the ozone layer, right? And part of the thing that we need to create tholins is UV radiation, which our ozone layer provides this blanket around the earth that filters out most of the UV radiation from the sun, right? Most of the things that are the highest energy, which are UVC rays. We still get UVA and UVB rays, which is why we have to wear sunscreen here so we don't burn ourselves, especially in Florida. But those UVC radiation, which we really need to create tholins, those are bounced back out by our atmosphere and by our ozone layer. So even if we did have the radiation here to make tholins, they're not going to last long because we do have that oxygen rich atmosphere. So it's going to start to break down and do its thing.
Fair, fair, yeah. Like it'll basically, even if we had that extra UV, it'll just create the next organic compound and create life again. So yeah, fair. Okay. So we did talk about though that there is possibly tholins that were here before our atmosphere became rich. I believe the from what I've learned, oxygen rose into the atmosphere about 2,300 million years ago. So quite a long time ago, but that was about the time when some cyanobacteria was really producing a lot of oxygen from photosynthesis. And at the time, there was a large enough oxygen sinks for them to take in the oxygen, and also some just iron and sulfides that were able to consume that and create oxides. But then it came to a point where the cyanobacteria was being very efficient in creating too much. So then it started going into the atmosphere. So
Yes.
prior to 2,300 million years ago, there's a speculation that there were actually tholins on our surface then?
Mm-hmm. Yeah. So when when the earth was cooling, right, you have all of these things like we talked about comets in space and things like that. We think that a lot of obviously earth was being bombarded by a lot of meteorites, projectiles and things, which is what formed our moon, right? Very
Yeah.
large projectile hit us just the right time and squish some of our stuff out there. But as we're being bombarded, a lot of that stuff that we would need, so some of those tholins or some of those compounds would be on the surface of our planet. And at the point where it was still very hot, there wasn't enough there to be able to do the things it needed to do. It wasn't until it started to cool that those really could start to form into what we needed, right?
Mhm.
To start building some of those building blocks. And again, we have to have the presence of oxygen to be able to start those processes. So they were just kind of sitting there waiting, ready, right, for those processes. And then again, once we started to build that oxygen, those could start to break down. They could start to make the alcohol groups, the amino acids, and the chains to start life. And then once we started building up more and more oxygen, right, and built up that ozone layer, then temperatures started to really regulate on Earth. We were starting to trap our heat and keep it, right? And then really that's when all of the conditions are right for life to really be able to thrive and to evolve in different ways.
Interesting. Yeah. So this is all to say really that tholins were potentially and quite likely the building blocks for organic compounds on Earth. Is that why it's so important for us to be exploring these other celestial bodies in our solar system because they could potentially look like pre-oxygenated Earth, basically?
Yeah. So it's nice for us. Obviously, we can't go back in time, right?
Mhm.
On our own planet and see where everything came from. But by looking at other planets, which we're always looking kind of in the past, right? Further out you go into space, the further back you're looking at time. So that's where looking at our own solar system, obviously, we can send things to those planets, to those moons, to those bodies in our solar system, and really get more information so that we can kind of look at things in the past in a way and kind of try to tell how we got to where we are. We're also looking at exoplanets as well, planets outside of our solar system, to see if there's anything out there that could be like pre-Earths that we can study as well, right? So we're looking at Tholins, yes, but we're also looking at many other ways that life could start. We're really trying to figure out all the different ways that life can start. So that way we know what we're looking for and we can kind of see the bigger question of, are we alone, right? Does all
Right.
life have to look like ours? Can it start in other ways? Is there life out there? So it can start in so many more ways than just the ones.
Because it would be kind of closed-minded and in one box to say, oh, there's just, the one way where how we were created. Obviously, that's what exactly we have to look for on different planets and such. But there's such a large amount and literally innumerable amount of planets and moons in this universe. So clearly there's got to be other ways for life to form. Very interesting. We were discussing earlier as well that there were some missions to explore Europa with the Europa Clipper. Are there any other missions we might be looking forward to in the near future?
So there is a mission that they're going to be sending to Enceladus soon as well. They're also sending a new mission to Titan, the Dragonfly. And there's also future missions to Titan that they haven't really kind of solidified yet, but there's hopes that they want to be able to take data from Titan because it is so similar to what we think Earth might have been like before it actually became what we know it to be today, that we want to take more data from that. That's one of the really promising spots for us. So right now with the Dragonfly, they are looking to send a probe there that will actually be kind of like a rotocopter, right?
Mhm.
That they'll put through the atmosphere and they'll be able to take data, but they want more of a presence too. And so in the very like far out future, kind of for the next generations of scientists, they're looking at trying to do a probe with basically three instruments. One that will be kind of a weather balloon that kind of always goes through the atmosphere and stays in the atmosphere of Titan. One that'll be kind of a floating island object that will land in one of the methane lakes so that it can always take data about the lakes. And then an actual rover that will land on the surface and explore the surface so that we'll always continuously be pulling back data, kind of like we do from Mars right now, right? We have all of these, this whole planet that's inhabited by robots, right? So many robots that we've sent there, but they're constantly bringing back data for us, right? So we kind of want to eventually do the same thing for Titan so that as it goes through its process of evolution, we can kind of see that as well and maybe in hopes learn more about our planet right? And how it started and how it is today.
Good. So we could definitely be looking for the Dragonfly mission you said. I
Mhm.
believe it's supposed to launch actually quite soon if they're going to stay on schedule, about 2028. And
Yes.
then hopefully we can see some more in-depth missions that'll be observing the lakes and sending a weather balloon.
Mhm.
It's all very exciting to look forward to for sure.
So Enceladus is kind of like Europa in the fact that both of those moons have very warm saltwater oceans underneath their surface, and they're both covered in ice. Europa is so close to Jupiter that it's icy, but you can kind of see the things that are coming up from below the surface. Enceladus is kind of hiding its surface and constantly reforming. It's close enough to Saturn that it has that tidal bulging too. The oceans are warm, but we have actually confirmed organic material that's coming from the geysers on Enceladus. So when we were flying by, we were actually able to take a sample of that and note that it was salt water. It is warm enough to support life, and there is organic material that is spewing out of those geysers, and it's happening fairly regularly. And so, because it's happening so regularly, that freezes in midair and falls back down on the surface of Enceladus as snow. And so it's completely covered in a new blanket of snow all the time, right?
Like a
So
winter wonderland. Okay.
so there could also be tholins just like Europa in those cracks, but we would not see them from the surface that way, just because it's always blanketing new snow over the top. So we do have plans to be able to send probes to Enceladus as well as Europa, right? To be able to look at, is there actually life underneath the surface of that moon right now? Because we have that evidence of organic material. So if there's organic material there, there's probably a good chance that there are things living underneath that ocean, which is very exciting to
Like
think
a
about.
hidden treasure box. Got you.
Yeah.
That's so awesome. Okay. Well, I think that's pretty much all that I wanted to talk about today, but do you happen to have any final thoughts for anybody who might be listening right now, or specifically why we need to study Tholins more?
Well, so studying Tholins more is really important just because we need to understand how life works, all the different ways that life works and how it can come together, just so that we know where to look, right? This
Mhm.
is a very exciting time to be a scientist because you have so many possibilities, right, out there in the universe. So once we can really figure out how that works here, close to us, where we can explore with probes and things like that, then we can apply that to other places in the universe, right? All these new exoplanets that we're finding, we can take that science and being able to look beyond our solar system to see, is there life elsewhere in the universe? So understanding this helps us to go further.
Awesome. Well, thank you so much for joining me today, Ms. Holt. And thank you guys all for tuning in and keep exploring and keep being interested in space.